Hello class, this is Mr. Johnson. I'm doing a lecture on Unit 6, single phase rectifiers. The purpose of a rectifier circuit, first of all, is to convert alternating current, which is sometimes called bidirectional current, into steady state or unidirectional, one direction, direct current. So really the difference when we say AC, that's alternating current, and DC is direct current. So we need rectifiers unless we're using batteries to get DC. We're going to use AC voltage to run in our plants our DC power. We're going to need to rectify that. So that's what we're going to discuss in this chapter. There will be three different types that we're going to cover. Single phase, which is half wave, full wave, and full wave bridge rectifiers. You can also rectify three-phase AC, and that is a chapter in your book, but we won't be covering it in this lecture. Okay. Now, after you rectify DC, we consider it to be pulsating DC. Now, if we want it to become what we consider smooth line or straight line DC, then we would have to add a filter, which is a capacitor, to the circuit, and at that point we would smooth out that pulsating DC into a good smooth straight line DC. Okay. All right, next slide. Some of the things we're going to cover in here is just an understanding of the rectifiers. We'll see how a half wave is constructed, how a full wave, and then a bridge rectifier. And these have one diode for a half, two diodes for a full, and four diodes for a rectifier. And then we're going to need to understand how to calculate the DC value of these rectified sine waves. All right. Okay. First type we're going to cover is a half wave rectifier. It's the simplest of all. Only requires one diode. Diodes, if we remember, guys, if you've studied diodes only conduct voltage, or I should say current, in one direction. They're a unidirectional component, and we'll talk a little bit about what do we have to do to them to get them to conduct. Okay. We'll see this in the next circuit. All right, so here, guys, I have my AC sine wave designated by the circle with a little sign inside of it. Here's my diode. I have both of the labeled components, the anode and the cathode. Cathode needs to be negative, the anode needs to be positive for it to conduct. We consider that forward biased. Okay, so let's first understand what truly distinguishes AC from DC. I know when I studied this, I kind of need to go back and just say, what makes this AC and what makes this DC? So I'm going to talk a little bit about it here. It's really distinguished all when in relationships to this reference line. And I've seen people that study this and then sort of forgot it, but guys, that's what's called the 0 volt line. In an AC sine wave, it's called a sinusoidal sine wave. It's alternating current. This voltage is never constant. As you can see, it's constantly changing until it hits what we call the peak, comes back to 0, goes into the negative side in reference to the 0 volt line, and then comes back up, and it continues to do this. Okay? So I have alterations in the plus side in reference to the 0 volt line, and on the negative side. That's what makes this AC. If I cross that 0 volt line, I'm AC. If we come over here, I have all my voltages above the 0 volt line, nothing crosses it, then this is DC voltage. I could also have these three pulses on the bottom. It'd just be negative voltage. Never goes to the plus side, it would be DC voltage. Okay? And that's really the difference between AC and DC. It's all in relation to the reference line. So if you'll just always remember looking at that, you should be fine. Okay? All right. I'm trying to get my pointer to work again. It keeps messing up on me. Okay? All right. And also, this diode is very similar to what we in hydraulics pneumatics consider to be a check valve. Check valve will only allow flow of fluid or either air in one direction. That's the same thing that a diode does. It will only allow current flow in one direction, only one direction. We call that forward bias when the anode's plus and the cathode's minus, then I can conduct. When I reverse that, I lose the ability to conduct. Okay? So right now in this circuit, you see my light here, my little green box. I am conducting because my anode and my cathode, in relations to each other, one is more positive than the other. And at that point, I will allow this sine wave to conduct on the positive half cycle. As far as this green line, you see that current is flowing from the negative through the load, through the diode, and back to the power supply. So at this point, this load will only see half of the sine wave, this top portion, when this is correct, negative and positive, and the diode is forward biased. But guys, if you'll watch the very next half cycle, this AC has now crossed below the 0 volt line, and now it's negative. What's happened is this negative and positive just switched. This used to be positive and negative, now we've switched. That puts the negative on the anode, the plus over here. This is a now reverse bias diode, and it will not conduct. You see I've lost my current flow. So therefore, guys, that's why this half of the sine wave is gone. I only see the top portion because I conduct half the cycle. I lose half a cycle, conduct again, lose half a cycle, and it continues to repeat. Okay? So this half wave rectifier only allows me to see one half of the sine wave. Okay? And that is the way a half wave rectifier works. Okay? All right, so now let's look at the next page. And now there's a few terms that we really need to start discussing when it comes in reference. And how do I read the voltage? How do I know what voltage is coming out of a rectifier? I'm putting AC voltage in, which maybe some of you have already been familiar. We talk about AC with in relations to the peak voltage of the sine wave, the RMS voltage. Those are two terms that we talk about pretty consistently when we're in AC. And matter of fact, guys, your AC, these meters that you have, those are RMS meters. When we read out of a wall circuit, that wall circuit is reading the RMS voltage. That's not as much voltage as in that wall. It's much higher, actually somewhere around 169 volts. That's the peak. But RMS stands for root mean squared. It's just some real fancy math that they have to do to come up with what is the voltage. What is actually, a lot of times we consider it the usable, I shouldn't say usable, let me see what I have in my notes. A lot of time we call it almost like it's the equivalent to DC. So I'm going to read what I have, some notes here. RMS is calculated the value of a constantly changing voltage of an AC sine wave, because you can see it's constantly changing. Sometimes we refer to this RMS to be the effective or the heating value, I said heating value, of an alternating current. And it's equivalent to the DC voltage that would provide that same amount of heat generation in a resistor as the AC voltage would if applied to that same resistor. Remember, AC voltage is always changing. DC voltage or DC current is always constant. So when you look at power, AC is moving all the time. It's always changing. It's always going back to the 0 point. So we have to have some way of trying to quantify what voltage, what effective voltage we have out of it. Okay? So when we're in AC, I'm going to flip back here. When we're in AC here, we talk about peak, and then we talk about the RMS value. And the RMS value is 0.707 of the peak. So whatever my peak value would be of this sine wave, I can multiply it times 0.707, and it would give me my RMS value. That's what you'll be reading with your circuit if you measured from a receptacle. Okay? Now back to this other term here, and it's called the average. And right here I have a note that says the average voltage of a single phase half wave rectifier is 0.3185 of the peak. So if I knew what the peak of that AC sine wave was, I could take that value times 0.3185, and it would give me this average DC value. Or I could actually know the RMS value of this sine wave and multiply that times 0.45. Okay, so two different ways I can go about calculating that voltage. So I'm going to show you, I think on the next slide, you will see how we will calculate it, right? So how to calculate the output voltage on a half-wave rectifier, and my AC source is 24 volts AC, so my transformer here is a 24 volt transformer, okay? So that's our RMS voltage. And the circuit is a half-wave rectification, just what you saw us just build. So what we could do is, using those two different methods here, I can say 24 volts AC, that's RMS, times 0.45, and that will give me my DC average value. Now, once I get that value, I have to subtract the 0.7 volts, and I'm sorry, that should say 0.7, not 0.07. That's a mistake on my part. But right here, guys, I have to subtract the 0.7. So let's talk a little bit about diodes. I think you've already learned this in your labs. A germanium diode, to turn it on, we have to have that voltage at about 0.3 volts. For a silicon diode, that same turn on or biasing voltage is 0.7. So typically in our rectifier circuits, we're using silicon diodes. So that's why you see us say take that minus 0.7. So guys, I'm gonna click out right here real quick, see if I can take me out of the show mode. No reason to leave that as a mistake. We'll fix it on the fly. Try to get back into this show, and we will turn on my little laser pen again and go back. So basically, we say 24 volts RMS times 0.45 minus the 0.7 volt drop, and what the load will see, that load resistor will see 10.1 volts DC. Or we could do it this way: take that same 24 volts times 1.414 to get our peak voltage. So we actually have on this sine wave, that peak right there is 33.936 volts. So I'm at the peak, and then I can take that voltage times 0.3185. Once I have that voltage, then I subtract my 0.7 diode the same way I did here, and it's the same 10.1. So you can see, guys, I can calculate that average voltage two different ways, using my peak or using my RMS value. And you see we just worked both of those out. All right. The thing I want you to hone in on is I put a 24 volt AC circuit or an AC signal across a half-wave rectifier, and my load saw 10 volts. So I didn't even get half of this voltage out. I got 10.1 volts. Let's watch and see how that changes for the next two types of rectifiers. Okay. So the next we're going to look at is our single phase full wave rectifier. So we're going to go from half wave to full wave. And I sort of want you to sort of look at this and pay attention to the wording full wave. We just talked about we're only rectifying half the wave on the last one. Then apparently this must mean that we're going to conduct and create output on both half cycles. And that is true. We will get both of those, okay? Now, it does require an extra diode. And one other thing that it requires, and you see I have it in red right here, is a center tap transformer. That's the big kicker on a full wave rectifier. You only have to add one more diode, which is not very expensive, but you do have to now buy a separate transformer, a different transformer that is tapped in the middle. And that is a little more costly than a normal transformer. So here, guys, I'm going to go ahead and show you. Here's the circuit. The input AC side is coming through my transformer, and at this point you will notice I have a lead up here, lead down here, and I have a center tap. So very center of this transformer. Transformers have turns on them, so let's just say this has 100 turns. At the 50 turn mark, we brought a tap out, and that tap is what we call a center tap. Okay, and when we're looking at that circuit, I want you to make sure this ground symbol, do you understand this ground symbol and this ground symbol? I could connect these together so they're both running to ground. So this path is a flow path from this point to this point. Okay? And what we'll have here is we'll still have this AC sine wave coming in. I'll have two diodes now. If you notice, I'll leave the anodes facing the transformer, and the cathodes are tied together. And those cathodes go into the load, and from the load goes to ground. Okay? So this is our single phase 2 diode full wave rectifier. Now I'm going to show you in a moment. This is a center tap transformer. So that means I'm not going to get the full voltage peak across each diode. I'm going to only get half of it. So I'll show you in a couple of drawings how this works, okay? So here is our full wave bridge I'm sorry, not bridge, but here's our full wave rectifier. And at this point, we have a negative down on B, a positive on A. And remember, this is going to always alternate, but at this moment in time, this is a negative, this is a positive. So at that point, what's going to happen is I have a plus on my anode of D1, and then there's a negative, more negative on the cathode side. So guys, this diode D1 is forward biased. This diode has a negative on its cathode, so it's not going to conduct. So guys, what will happen here is when I'm in this part of the waveform, as this AC alternates and sets this transformer up with a negative and a positive, what's going to happen is I'm going to conduct from C, from this lead, it's going to go to ground. It's going to come back up through the ground, go through the load, and back to the plus side through D1. So I conducted current from C to A. D1 was on. Okay? The very next half cycle, it's switched. And if you notice, you can see them changing. This plus is back at the top. And now I have put the plus at the bottom. The sine wave went below the 0 volt line. So now I have a negative to the plus side, or the anode. But now I have my plus side down here to my anode. So now D2 is forward biased. D1 is reverse biased. It can't conduct. So once again, I will conduct current from C through the ground, up through the load, and then back through D2 to my plus. I'm always trying to get from a minus to a plus. This so happens I'm going to go from C to B. So this time I conducted the second half cycle. So yes, the half wave only conducted one half cycle. This full wave, we just got both half cycles. So here's a picture of the output. So I want you to look at this. This is very important. This here was the full peak of the secondary in this picture. But if you look at the half peak of the secondary is all I get through to my full wave rectifier. Okay? I don't get this giant